Sí, 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 sí.
Ouais, je vais te l'envoyer dans le chat, fait qu'au moins il y a un lien. Et voilà.
Entonces, usted está grabando desde su computadora y va a tener usted en el live.
No entiendo. Yo estoy grabando. El que tiene el Zoom está grabando. Lo está grabando allá.
Pero alguien tiene que grabar.
Sí, están grabando ellos, ¿no?
Sí, estoy grabando.
Ah.
Todo como está. Well, good morning, everybody. We are short. Ah, sí.
Ya está.
Yo tengo el...
Ya está.
Yo tengo el... No, está cerrado.
Ya está. Él tiene que estar.
Claro. Ya muera.
Es el.
Que silencia todo el mundo.
Yo no estoy conectado.
Menos
No estoy conectado solo.
No.
No.
Ah, ok.
Esto que el John no funciona en
no, sí funciona. Lo que pasa es que hay alguien está en conflicto. Quiere poner silencio a todo. No, funciona. Lo que pasa es que hay alguien está. Orlin. The first part has to do with the Leonard Research Prize given by the Interciencia Association, which, as you all know, is a federation of. The first part has to do with the Leonard Research Prize. Sorry, one minute. Oh, oh, yeah? Sorry, one minute. Hello? Yeah. Yeah, it's deactivated. Here. Okay. No, no, it's in silent. Well, let's try again. Very good. Good morning, everyone. The Interciencia Association, a federation of scientific organization of the for the advancement of science in the Americas. Is proud to present the winner of the Leonard Research Young Scientist Award 2022, which is in this edition dedicated to physical sciences and materials. With this award, a young scientist is recognized for his career and valuable contributions to scientific or technological progress of at least one country in the region. The award included the participation of candidates from 5 countries: Argentina, Bolivia, Cuba, Mexico, and Panama. The jury for this edition was made up of 3 renowned scientists with extensive experience: Dr. Roberto Cisler from Argentina, Dr. Germán Pérez Alcázar from Colombia, and Dr. Gerardo Herrera Corral from Mexico. The jury evaluated the applications of the participants according to the institutional impact of the scientific technological work carried out in their country, the quality of and quantity of the original scientific production, the quality and quantity of the human resources trained, and the regional impact of the carried work. Given the outstanding scientific career of Dr. David Bermúdez from Mexico in the Instituto Politécnico Nacional, and his important role in the training of human resources and work in this the dissemination of science, he is considered with sufficient merits for a special mention of the Leonard Research Award for Young Scientists 2022. We have a plaque for him, and we are going to ask Dr. Alma from the delegate from Mexico to receive it. The Vice President will give the prize, the certificate plaque.
Yeah, thank you. Thank you very much. David Bermúdez Rosales is an excellent science in Mexico, but it's also a good friend of mine. He's even younger than me. And so I think that he really deserves this recognition. And I am sure that in a near future, he will be a winner of these and other awards. Thank you so much.
Thank you, Dr. Alma. by virtue of the excellent track record and scientific research in the field of molecular magnets and his contribution to science and academia in the country, in his country and the region, he was, once he was reinstalled in Panama, the jury considered as a winner for this prize, Dr. Eufemio Moreno Pineda from the University of Panama. He's worthy recipient of the Leonard Research Award for the Young Scientist 2022. The award involves an endowment of $2,000 American dollars, which were already transferred to him, and a recognition plaque. We will ask Dr. I'm going to ask Dr. Panama, see? Yeah. and yeah, of course, it's their work. So we are sorry that Eufemio had problems to come as was initially proposed to Canada, but he's with us via Zoom, so he will deliver his talk accordingly. Dr. Eufemio, could you connect
Yes, I am now.
to the Zoom? Yeah,
Shall I-
okay,
yeah, I am connected now.
you can start.
Okay, thank you very much. I am really pleased and honored to receive this prize. Actually, it's a prize that I receive it, but there are many people who actually work on this, which could well receive this as well. And now I will present you with a small summary. I cannot share my screen. Can you give me, please, access?
Yeah, we can see
Perfect.
everything.
No,
Very good.
perfect. Thank you very much. Yes, now I will give you a small summary of basically my work the past 12 years, basically. Most of this work has been done in Europe. I did my doctoral and master studies in England, and then postdoc also in England, and then I moved to Germany, where I did most of the work I am going to present here. And since I returned to Panama in 2019, at the end of 2019, I have been trying to establish this field of molecular magnetism in Panama. So basically, this is just a short summary of what I have done, what I have been doing, and what I'm continuing here in Panama in collaboration with different researchers here in Panama and also in Europe. So basically, what I'm going to talk today is about quantum information processing using magnetic molecules. I am a chemist, actually, but I have been trained in the field of magnetism, molecular magnetism, which involves the synthesis, structural characterization using different techniques. Mainly, I would say single crystal X-ray diffraction and several techniques for the magnetic characterization, including theory, okay? So the techniques I use mainly are squid magnetometry, superconducting quantum interference device magnetometry, the conventional one, which goes from 300 Kelvin to 2 Kelvin, and then micro squid studies, which is a highly specialized measurement, which goes down to 30 millikelvin, which allows to measure some quantum effects, which are of paramount importance for the application of these molecules in quantum information processing schemes. These molecules, I will start basically with a short summary of what are these molecules. These molecules actually were discovered by accident, I would say. This is actually the goal of at that time in 1990s. So the study was to understand the photosystem too. And this is something I like to say when I give talks, because actually a great amount of science and the important discoveries are made basically by serendipity. It's just accident. Some people are looking for something and then they find something interesting in a totally different area, open a new area. And during the quest of understanding the magnetic properties of the photosystem 2, to understand how the photosystem 2 works, what they found is that they found a peculiar behavior. They found that this molecule, this is manganese 12, as a manganese acetate inorganic complex, show hysteresis opening. So basically a behavior that was not common at all for molecular system. Actually, it was not expected because magnets, in general, conventional magnets, they work basically in certain cooperative way, okay? Shockingly, the system at molecular level, that means even in solution, there was just even isolated molecules were able to store information or show hysteresis loops. And this opened basically a new field, the field of molecular magnetism, in which at the beginning, all the researchers try to get better systems with larger loops, larger energy barrier to relaxation, because of a simple goal. I mean, the aim was to get a larger hysteresis loop because it was calculated that if a typical tape, in that time 90 minutes tape, you know, these recording tapes of those times, were made of this molecule, instead of storing 90 minutes of music, it would have been possible to store 150 years of music. So the amount of data that could be stored in one of these systems, or a data storage device made of molecular system, would be way better than any conventional system. So basically the field started with this molecule, and the goal was to obtain clusters of 3D metals, transition metals, where the anisotropy axes were aligned in order to get a larger hysteresis loops, okay? The field went on for almost 10 years with no major improvement on the magnetic property, the physical property of the synthesized complex at that time. However, in 2003, a major discovery was made when a researcher called Ishikawa from Japan found that it was not necessary at all to get a cluster of transition metals to obtain a single molecule magnet. These molecules are termed single molecule magnets. But he found out that just a single lanthanide ion, it was enough to get a large hysteresis loop, larger, 10 order of magnitude larger energy barriers compared to the transition metal analogs, and even to observe quantum effects, okay? So basically, these results open a new field, or basically rejuvenated the field of molecular magnetism, because instead of looking at polymetallic systems, which were a bit difficult to obtain with all the anisotropy axes aligned, it was possible to obtain just a single ion complex with way better characteristics. And since then, this system has been proposed in several applications, okay? Several applications. As I mentioned at the beginning, high density data storage devices. They have been proposed for quantum information processing. The long sought quantum computer is still an extremely important area of investigation nowadays. Molecular coolers, quantum sensing, quantum simulator, and so on. Among all these possibilities, I'm going to give a small talk or a brief information about of the research I've been doing in two main parts, which are molecule for data storage devices and quantum information processing, okay? Data storage devices. What do we need of data storage devices? Basically, what we need for data storage devices is large hysteresis loops, because in this hysteresis loop, basically what we can do is that we can save the information in one of the two states of the system. Let's say just arrow up or arrow down, if we want to consider in this way. And if we have a massive energy barrier for the reversal of this arrow up to down or down to up, then we can store a lot of information for a long period of time. We know now that because we can store the information in a single molecule, we can store way higher density than conventional system that depends on the grain size, okay? Now, the problem with these systems is that although they show hysteresis, the hysteresis are that we can observe typically are at a really low temperature. For manganese 12, which was the first complex to show this hysteresis, the barrier was around 6 Kelvin. So above 6 Kelvin, you couldn't see any hysteresis. And then with lanthanides, it was found that even though the energy barrier are really high, energetically really high, there is too much quantum tunneling. I will talk a little bit more about tunneling in a bit. And the problem is that quantum tunneling of the magnetization is a non-thermally activated process, which allows the reversal of the magnetization just because of there is a mixture of the wave function in the ground state, okay? And this is not good for data storage devices. So typically, although this is an extremely nice example of a well-behaved system at relatively high temperature, okay, 75 Kelvin is quite high for a single molecule magnet. The main problem is that most of single molecule magnets do not show this kind of behavior. So one of our goal was to try to understand how can we improve this, okay? Several researchers have thought that the problem was the nuclear spins, because the nuclear spins can help the system to couple to the nuclear spin bath and help to the relaxation. So following this, what we try to do is try to understand how chemically we could remove the nuclear spin of the system, okay, and see how the nuclear spin actually influence the magnetic property of the system. In theory, before this study, we were considering that the nuclear spins were actually helping to enhance the quantum tunneling effect, okay? So the first thing we did is to synthesize a single molecule magnet. We needed to study a single molecule magnet, okay? And we needed to know more or less how the nuclear spins influence the magnetic properties. So for this, we synthesized two isotopically enriched lanthanide complexes, okay, dimeric complexes. One with 163 spin, nuclear spin 5/2. The other one with 164, dysprosium 164, non-nuclear spin. So okay, so the characterization, crystallography is the most important technique for us because we need to know the relative orientation of the molecule in the unit cell, and also it's important for us to understand where is the anisotropy axis lying inside the molecular structure, okay? So as you can see here, we have this arrow representing magnetic anisotropy for both dysprosium ions in the molecule, and these were obtained by KCCF calculation. I will say a little bit about this later. Now, the main problem is that when we do hysteresis studies, what we want to see, ideally, is a large hysteresis like the one I showed you before. Unfortunately, for single molecule magnets based on lanthanides, for F-lanthanides, the loops are quite shallow, quite narrow at zero field, near zero field. And this is basically ascribed, or has been mainly ascribed to quantum tunneling of the magnetization. In this case, we do see again tunneling, even when removing the nuclear spin, although we can clearly see that the opening is slightly larger for the 164, which has no nuclear spin compared to the 163. So the question is how is actually the tunneling being affected by the presence or absence of the nuclear spins? So in order to understand this, we first set up a Hamiltonian where we can actually simulate the Zeeman diagram corresponding to the derivative of the magnetization of the hysteresis loop at 30 millikelvin. Well, this is the temperature dependence of the hysteresis loop from 30 millikelvin to 1.3 Kelvin. And we see clearly that we can actually reproduce the crossing, which is where the system tunnels quite well. And this helps us to then follow and move on to the one with nuclear spins. What we find is that indeed there is an important nuclear spin hyperfine interaction contribution and also a quadrupolar contribution for the system. But the most important results actually is that when we do the simulation of the hysteresis loops or the magnetization loops with and without nuclear spin, what we find is that actually the tunneling, basically there is a tunneling gap, there is a small opening that tells the system basically describe the system or describe how much the system tunnels at that specific crossing. What we see is that the tunneling is unaffected by the nuclear spins. Okay, it's totally unaffected by the nuclear spin, which means that most efforts to try to reduce quantum tunneling by replacing the dysprosium ion without with nuclear spin by one without nuclear spin actually were not well founded. What we found is that the tunneling is totally independent of the nuclear spin, and what it does actually, the hyperfine interaction, what it does is just smear out the tunneling probability to a larger field instead of a specific value. Okay. Importantly, when we move on to higher temperature, in the microscopic data, we went from 1.3 Kelvin down to 30 millikelvin. Now, when we do the studies from 2 Kelvin up, in this case to at 18 Kelvins, what we find is that the behavior is completely different. Okay, and here you can see the figure on your right, on your left, sorry, on your left of the screen. What you see there is the magnetic susceptibility behavior for the two systems, and we can see clearly that there is an important difference between the 163, the system with nuclear spin, and the one without any nuclear spin. And when we do the relaxation time versus temperature, we can clearly see that at zero field, the system with the nuclear spin is well characterized by a tunnel by quantum tunneling, where you can see clearly a temperature independent plateau. Okay, which is the orange orange symbols, while the greens are quite temperature dependent. Basically, this what is telling us is that the tunneling for one system is totally different compared to the other one. This seems to be counterintuitive, but actually it's not, because what the system is doing is actually the system with the nuclear spin can tunnel more, because now we have more events happening a larger field range than compared to the one without nuclear spin, which is actually shifted to higher or lower fields. When we, instead of mesh collecting the data at zero field, okay, with a DC direct current field at zero, we move it to 30 millitesla, where more or less is the crossing for both systems, which is arises from the interaction between the systems. Then we can clearly see that the behavior is exactly the same for both of them. Okay, so this is important because most of the works at that time that were considered and the tunneling would be diminished if we will remove the nuclear spin were actually not well founded, because actually they were looking at the tunneling events at a place where they were not actually happening. When you put the tunneling event in the right place, basically it doesn't matter if it was with or without nuclear spins, the system, both of them will tunnel equally. Okay. Another important aspect is that what we found is that despite the tunneling being the same, we could see in the hysteresis loop that for the one with nuclear spin, it was more temperature dependent. Okay. This let us wonder why it was more temperature dependent, the system for the complex with nuclear spin than the one without nuclear spin. And for this reason, we did a small simulation considering the coupling or basically the relaxation time versus field when considering a system with and without nuclear spin. Without nuclear spin, we found that we just in this moment we just study an ideal system with just 1/2 nuclear spin, and what we found is that indeed the nuclear spin from this ideal system seem to couple better the relaxation to the basically the magnetic property of the system to the phonons, which would help to the relaxation for the system, which is not good actually for data storage devices. So at that time, that was the first work, well, one of the first work, and then what we continue studying where was the temperature dependence and the field dependence and the time dependence of the magnetic behavior for a terbium PC2 complex, which is basically the first system to show, the first lantern system to show magnetic hysteresis loop for these kind of complexes. And recently, what we just basically published is that when we do the thermalization study, when we study how the Boltzmann population for the nuclear spins evolve during time while correcting the system and the magnetic data, what we see basically is that first of all, tunneling can occur in all these crossings if there is not the quadrupolar term is not well aligned with the magnetic axis of the electronic system, okay? And secondly, what we found is that if we prepare the system, all the nuclear spin, the Boltzmann population for all the system at the beginning, equally populated, what we find is that during the evolution of the time, okay, during the time evolution, we could see that they actually do not stay equally populated logically because we are working at really low temperature. So the higher in energy states will get less population, will be less populated than the one at a lower energy. But the most important thing is that we also observe that for the ideal case of a quadrupolar term which is aligned with the electronic moment of the system, we could see that the selection rule still is plus or minus 1. Okay, this is because in some cases we could see even plus or minus 2, plus or minus 3 selection rules for this one, which are not typically obeyed, and it's because of the alignment of the quadrupolar term. Okay, now what is the most striking result of this? The most important is that when we simulated the lifetime, the transition, the lifetime of the system, the tunneling, the lifetime of the system versus temperature in a long temperature range, which is a large temperature range, which is from 50 millikelvin up to 500 millikelvin. Okay, what we found is that the nuclear spins actually are not there in an innocent way. Actually, the nuclear spins help the system, the electronic system, to couple better to phonons, hence producing more direct relaxation. So basically, what I want to say here, to make a small summary on these points, is that although tunneling is a fixed quantity, which still we do not understand completely why occurs, the nuclear spin do not actually improve it, enhance it, or decrease it. They are just there smearing out all the tunneling which typically occurs a single value, a single point, okay, a single crossing at a single field. However, the nuclear spin do help to the coupling to phonons, which is a major problem because at low temperature acoustic phonons are really active and they can help to the to the system to relax, which is not good for data storage devices. Why? Because if we want to save some data, we don't want to wait 2 days and then we have lost the data, right? We want to have a system which can store the data for a long period of time without losing the information. So this is the most important aspect, I would say, of this thermalization work. Okay. Now, what is we also have been trying to understand how we could use single molecule magnets for data storage devices, but not just in bulk, because in bulk we have phonons, and this is a big problem. In bulk we have too many phonons which we cannot control. It is difficult to reduce how the system couples to phonon. So a way to avoid this problem with phonons is to reduce the phonon bath. Okay, and how can we reduce the phonon bath? Well, simple. We can use a single molecule in a system located in a place where phonons are less pronounced. Let's say there are less phonons to available for the system to couple. And in this case, there is a technique which has been exploited and proposed for a long time, and there are many important people working on this field, which is single scanning tunneling microscopy. Okay. With STM, it has been shown that it's possible to read out the magnetic properties of systems, okay, molecular system, magnetic systems, but also to manipulate them. Okay, there is a work where actually just by a spin polarized STM equipment, and by applying some voltages, it is possible to flip the spin, the electronic spin of system. Okay. Now, one of the problems when working with lanthanides is that lanthanides, they have a really inner F shell, and because of the inner F shell, they do not communicate much with the environment. Okay, they do communicate, but they do not communicate that strongly. Okay, in that sense, using STM is a good way because we could try to manipulate a single molecule, so we restrict the number of phonons available to the system. The bad thing is that then how can we read out the 4f electrons if we cannot perhaps observe it? Okay, so in this case, we study a dysprosium PC2 complex, again, a single molecule magnet system. And the important aspect is that this complex in its neutral form, it has an electronic spin coming from the lanthanide, okay? But also it has an electronic spin coming from the ligand, which is a radical, so a spin half. The important aspect also is that these radicals can be observed directly in STM through the Kondo effect. It's just a strong signal when you couple a magnetic impurity to a conduction electron, okay? And what is important here? The important aspect here is that when we do the field-dependent study of the Kondo effect, the Kondo peak for this system, what we observe is that the Kondo peak moves, gets bigger, actually, splits in two, and then depending on the field, the splitting of the Kondo peak is larger. This tells us directly that although the Condor resonance observed in the spin polarized STM arises from the electronic signal of the radical, actually this electronic signal of the radical is coupled to the magnetic properties of the 4f electrons. Okay, there is an interaction between the 4f electrons and the electronic spin of the radical, which allow us to basically indirectly read the 4f contribution of the dysprosium ion sitting inside the molecule. Okay, so we can demonstrate this by simply simulating the magnetic data, the magnetization data for the whole system by considering this splitting, obtaining the interaction that the interaction that couples the electronic spin of the radical with the electronic spin of the lanthanide. In this way, we can actually easily prove that we can indirectly read the 4f magnetic properties of the dysprosium, despite not observing it directly in the STM experiments. Okay, so in this work, basically, this is what we show. We show that it's possible through the interaction between the lanthanide and the radical. It is possible to read out the magnetic properties of the lanthanide, which are really shielded, but despite the shielding, still, because of the coupling, it's possible to read it out by STM. So it's just basically showing that STM is a plausible technique to exploit as for single measurement of single molecule magnet. Okay, and devices, even devices. Also, another recent work has been to try to control. It's important that when we work with data storage devices, we want large hysteresis loops. But also it's possible to use these two states up and down as switches, okay? As switches. So in this sense, what we do is that we did synthesize a lanthanide complex, okay? Again, it's an inorganic complex which shows large hysteresis, large hysteresis, no, large anisotropy. And the important aspect of this system is that by simply adding some solvent, it is possible to oscillate between the two different complexes that can be formed. The solvated system, the one in blue, the solvated system, and the red one, which is the unsolvated system. We did the characterization with Raman and also illuminescence, and we can see clearly that by adding THF just with a pressure. It's not necessarily to add the liquid directly. If there is a pressure of THF in the sealing tube, it's possible to go back and forth between the two states. And then these automatically tell us that we can actually use it as some sort of switch for any application. Of course, we are typically more interested in the magnetic properties than in the vibrational spectroscopy of this, vibrational spectral of this system. So what we did is that we did the experiments, also the magnetic studies for the erbium and ytterbium complexes, which were these ones that show more anisotropy. Okay, and what we found is that the erbium complex, when is unsolvated, when there is no THF solvent around it, it has a really massive hysteresis loop, which we published in 2019. Okay, and when we add some THF, okay, some solvents, then the magnetic properties get really diminished. It goes from 361 Kelvin and large hysteresis loop up to 12 Kelvins. It goes to 96.7 Kelvin with no opening of the loops. So basically, what is telling us this is that we can actually prepare through a chemical synthesis switches, molecular switches based on single molecule magnets. More relevant is actually the neodymium complex. The neodymium complex, we can actually switch between no SMMs, no SMM behavior whatsoever, to an SMM profile. Okay, and then of course this from the chemical point of view, open the possibility to creating switches just by engineering the periphery of the lanthanide in a correct way, basically. Okay, in a correct way. So this is what we actually found, and is interesting because it's not just about the magnetic properties, but also the Raman characteristics and the luminescence. One of them is for some of them, the cerium and terbium, for example, they are luminescent when they are in the solvated form, but not luminescent when they are not solvated. Okay. Important. I mentioned it, but I haven't gone into detail. The green arrow, or the arrows you have seen up to this point, basically they are the anisotropy axis, which can be calculated easily using CASCF, which is a calculation, an ab initio calculation, complete active space cell consistent field calculation, which are really important because typically obtaining experimentally the axis of this system is not a trivial work. Okay. So this was basically my first part of the talk, showing that a molecular system can be actually systematically controlled, engineered, so that they can actually be part of data storage devices. And of course, some understanding of the key properties of this system in order to get better behavior. However, I would say that one of the most relevant part of my talk, and actually the field of molecular magnetism, is the exploitation of this system in systems in quantum computing. Okay, quantum computing, which is quantum information processing. Quantum computing, well, perhaps you have already heard about quantum computing, and it was proposed in 1980 by Richard Feynman and others, where he said something simple. He said, if we want to simulate something which is quantum mechanical, we need quantum mechanics. Okay, it's simple, nothing else. Since 1990, in 1980s, basically the field stayed dormant for quite a long time, until 1994, 94, I would say, where Peter Shor, a mathematician, showed that if we could use quantum mechanics to describe physical systems, we would get faster results in comparison to the classical physics. Okay, so in this case, Peter Shor developed a quantum algorithm to factor very large numbers in a polynomial time. Okay, nowadays all the bank systems work on factorization of large numbers. Okay, and that's why they are relatively secure, because factorizing prime numbers is not an easy task for computers. However, he showed that we develop a quantum algorithm, it will be much faster. In 1997, then Gruber, it was basically mainly theory. Love Gruber proposed a quantum algorithm to find an item in an unsorted database in a square of number of entry time, which will be a lot faster than the typical time. The point of this is that quantum computers are supposed to be way better than classical computers. Okay. Nowadays, this is an active field. There are many consortiums working a lot on this. NASA, Google, IBM. There are several companies investing a lot of money, Intel, on a quantum computer, because the advantages of quantum computer will surpass any classical computer. For example, simulating properly quantum mechanically a protein is impossible nowadays. What we typically do is that we do mix, basically, a mixture of two different systems, two different approaches, a classical approach and a quantum mechanical approach where is needed, actually. Okay, so but then experimentally, what can we do about quantum computer? Well, experimentally about quantum computer, what we can do is that we can design the building block of a quantum computer, and the building block of the quantum computer is also the building block for a classical computer. Basically, this classical computer work with bits, a quantum computer work with qubits. The difference in here is that qubits, instead of having just two states, 1 or 0, in a qubit you can have 1, 0, and the superposition of states generated by the system. Okay, this gives the quantum computer a much faster, a larger Hilbert space for to do the calculations. So instead of scaling up the computer by increasing the number of cores, as we typically do, just with the number of bits, it would be way better, the increment that will be gained, actually. Okay, so which qubits are being proposed nowadays? Well, some of them are MV centers, superconducting, trap ions, several systems, and among those we have molecular system. Okay, molecular system. So what can a what should the qubit, what property can it should it have? Okay, basically the qubit should fulfill what is called the so-called the Vincenzo criteria, which are well-defined basically properties. And the most important thing is that once you have a qubit, it should be possible. We should be able to link them. Okay, so that there is an interaction between them, because that's the way quantum gates work, by interaction of bits. Okay, in this sense, molecules have shown all these properties, all these so-called the Vincenzo criteria. But the most important aspect is that we can also engineer the periphery and also interlink them together by chemical means. For us, in chemistry, basically, is not complicated to design a ligand that can couple two different qubits, okay, and bring them together at a fixed distance. This is one of the major problems with MV centers, for example, because MV centers are extremely nice system showing really nice properties, but one of the most important difficulties is that it's not possible to put an impurity of any MV center in a fixed location all the time. Okay, the distances are really, let's say, random in some cases. Okay, so in this sense, I also had the privilege, and I was lucky to work in the lab where most of these implementation of molecules for quantum computing have been studied, have been applied. And in this sense, I will talk a little bit about the nuclear spins embedded in single molecule magnets. Okay, in this precise case, for us, it is important that the tunneling is present. We don't want to get rid of tunneling, not for quantum information processing. Actually, quantum tunneling helps for the readout, initialization, and manipulation of the electronic properties. Okay. The field, basically, or the goal is to synthesize molecular systems that behave well, put them in an hybrid device, in a transistor configuration. And in this transistor configuration, it is possible to read out and manipulate the nuclear spins embedded in the system. Okay, this has been shown by my previous boss, Wolfgang Berndorfer in Germany, and they have really nice results on this, showing that it's possible to actually apply this technique to do quantum computation with a molecular system, with single molecule magnet. More relevantly, I would say, is that they show in a proof of principle study in 2017, they showed that it was possible to do the Gruber algorithm experimentally, okay, with a single molecule embedded in a transistor shape. So based on this, what was our goal? Well, when we exploit nuclear spins, the important aspect is that with nuclear spins, we have several nuclear states, okay? And these nuclear states can be exploited for quantum computation as quantum bits or multi-level quantum bits. The Gruber algorithm that was executed by these researchers was possible because in a single molecule, all these states were available. Now, if you want to increase the number of calculations that can be done in a single molecule, then the logic way is to increase the number of nuclear spins available for the system. And this is what we set up to do here. And it was to basically create a molecule, engineer the nuclear spin inside the system, so basically include a larger nuclear spin inside the system, and see if we could read out the nuclear spin by a microsqueeze technique, the microsqueeze technique. Okay. In here we have a single molecule magnet. For us, it's always important to know the relative position of the molecules inside the crystal in order to establish a good Hamiltonian to simulate the properties. We see the hysteresis loop, and what we were looking for is actually well seen here. We see a lot of events, a lot of tunneling events present in the one with nuclear spin. We prepare also the one without nuclear spin just for comparison. Okay. And the most important aspect is that when we do the derivative of the hysteresis loop, we were able to observe all the different tunneling events occurring for the system. So basically, just by changing the nuclear spin of the system for 3/2, which was for terbium in the Gruber algorithm, to 5/2 of this Procyon, we were able to increment the number of states available for computation. Okay, for computation. So what we show here is that it's possible to increase the Hilbert space available for computation just by changing the nuclear spin. Another way, which arises because it's impossible to continue increasing the number of nuclear spins present in nature, is to actually couple two different systems with nuclear spin through an electronic interaction, and this electronic interaction could create an indirect pathway of communication between the different nuclear spins. Again, we synthesize a system which is a single molecule magnet. In here we see in the kite it goes up, and it is because there is a ferromagnetic interaction, meaning that there is an interaction between the two electronic spins. And the important aspect, always the 30 millikelvin studies or the microsqueeze studies at low temperature, and we can clearly see again all the different steps. And these steps arise from tunneling, okay? They stem from tunneling. And the important is the most important information here is that by just setting two different spins, two electronic system with nuclear spins, with an interaction between them, operating between them, it is possible to increase the Hilbert space, the space available for computation, from 4 to 16. Okay, so now in this system, it's possible to create or carry out larger calculations because we have 16 available states for computation. Okay, logically, once we have a nice system showing interesting behavior, what we do is we proceeded to the integration of this system in a spin transistor device. Now a single molecule. The previous study were done in a crystal and assembled. Now in a single molecule, we can create a spin transistor system and try to read electrically the nuclear spin of the system. Okay. What we found is that indeed it is possible to read out of the nuclear spin of the system indirectly when the system tunnels through the crossing, the avoided crossing, and it was possible for us to read out all the different states available for computation. Okay, this basically demonstrates that it's possible to, one, chemically engineer the system, and two, put this system directly into a spin transistor hybrid device and read out the magnetic properties, which is the, let's say, is the previous step to the execution of a quantum algorithm. Okay. And finally, I will go quickly through this one. Another important aspect is that when we don't have any more ways to increase the number of states available through changing the hyperfine, the nuclear spin of the system of the lanthanide, and we reach this limit of coupling the different systems, then we can do more chemistry simply. Okay. And in here, what we did is that we study simply two different radicals coupled to different tethers, three different organic tethers. And the goal is basically to see if there is a communication between the two different radical moieties, and exploit this communication, or see how the magnetic properties concerning these two different entities coupled behave for quantum computation. Okay, so in this case we exploit mainly APR spectroscopy, and in the APR spectroscopy we were able to observe really good relaxation times. Relaxation time basically is the time required to do a calculation without losing the information, and we went up even to 95 Kelvin, meaning that the information of a single qubit is preserved even at high temperature. Okay. Now the question is, what is the effect of having two of these couples together? Well, the effect of having these two couples together is that in one of them, C1, which is the shortest one, it was possible to induce Rabi oscillation. Basically, Rabi oscillation is the manipulation of the electronic spins for the coupled system. When the organic molecule was too long, then the system behaved like two isolated radicals, while when the distance was short, then we had the coupling of the two, leading to a spin plus or minus 1 and 0. And this line that you see here, which are the different colors, basically these are the oscillation between these two states, implying that it is possible to employ this approach to create quantum bits or quantum gates also, just through chemical engineering of the system. Through DFT calculation, it was also possible to see that basically the coupling was because in the shorter ligand complex, there was spin leakage, and this spin leakage led to interaction between the two moieties, leading to the coupled behavior, which was the one that we were looking for. So basically, with this, I just wanted to give you a brief information about what I have been doing and what I'm trying to now do here in Panama in collaboration with several researchers, very important. And these are two of the several different fields in which single molecule miner can be applied. Okay, and with this, I want to thank all the collaborators, mainly in Germany and France, and of course here in Panama for funding, and all of you for your attention. If you have any question, I'm happy to answer.
Thank you very much, Eufemio. Fantastic and very complex work you have done so far. Myself, I am so proud of you. Because he was my student, and now he's my colleague. So, and this work he has shown, he had been doing in the last few years, is in the frontier of knowledge. So it's something out of my actual capacity. So, but my understanding tells me that you have done quite wonderful work, and I understand why you was chosen as winner for this prize. If someone has a question or a comment, it's welcome. No question? Well, no comment. People are abrumated by your word. But now I do have a question for you. You have shown a lot of complexes that have this single magnetic molecular behavior, but all of them practically were lanthanides. Do other type of elements show these magnetic behaviors?
Yes. Transition metal complexes, they can show also SMM behavior. We focus on lanthanides because when you work with transition metal system, typically you need to try to synthesize clusters, several ions together inside the molecule. And on the top of that, you need to try to be careful because you need to force the system to have the anisotropy axis aligned. Okay? So if they are not aligned, like in a vector, they can cancel and you cannot see anything. So these are the complications with transition metal systems. You need to have the anisotropy aligned, and then you have a cluster, you have to have good interaction between the systems. So this creates a lot of complication. We focus on lanthanide mainly because we can work with just a single lanthanide, okay? And the anisotropy is already inside all the lanthanides. There is no need to have 2-3 different lanthanides to have the same anisotropy, okay? In different collinear anisotropy. That's why we focus on lanthanide. With transition metal, it's possible to have also single ion system showing SMM behavior, but the problem is that typically these systems are not very stable, okay? There are several iron complexes which show SMM behavior, really nice, single ion, but then they are really air sensitive, moisture sensitive, so it's complicated to use them and implement them in application, which is actually our goal. Our goal is to try to get a nice system that behaves really well and to try to deposit it on the surface. With systems which are so unstable, is almost impossible. So yeah, it's possible to answer your question. It's possible to have it with transition metals, indeed, no problem, but it's more complicated. Somehow also up to this point, what we have seen is that the magnetic properties are not better than lanthanide, not normally.
Thank you very much. Well, I just have one comment. Your work is being done in Panama, but with the cooperation, international cooperation with people in Germany, mainly France and England. But probably you will. It's not to be answered now, but I would like to propose you to look for partners in Latin America. Probably you will find some people in Latin America, in Mexico, and Brazil, Argentina, that can go along with you in doing this research. It's very interesting and very important for the scientific community of Latin America. Thank you very much. Thank you very much.
Thank you very much.
Well, now we'll have a little break, 10 minutes, to relax too many physics, too much physics. Thank you very much, Femi.